All right, this video is for Calculus AB for our snow day. Just thought I'd give you a little example to work through. Here we'll do a couple of things. We'll do all the questions that are listed here, and we'll probably just kind of mess around with this a little bit too, and try to do a few other things as well. So I encourage you here to pause the video and take a look at question A, which says find the area of region R. And so pause the video, play again here in just a second, and I'll show you a solution. Okay, so to find the area of region R, you really have a couple of choices here. You could use vertical representative rectangles. You could use horizontal representative rectangles. And I think either one of them would work just fine. And really, honestly, I think just for you to get kind of the full picture of things, I think that it'd be cool if you did both. But I am going to suggest one of them here for this one. And I'm actually going to suggest not using horizontal representative rectangles because, although it would be doable, if you did, you'd find that it's more complicated than it needs to be. And here's why. If I did horizontal representative rectangles, please notice how for the upper half of the region, so basically from this dotted line up, the representative rectangle's length dimension there would be represented or would be determined by the y-axis on the left and then e to the negative x squared on the right. And then below the blue line, the blue dotted line, that would switch. So on the right side, it would then be y equals 1 minus cosine x. So very doable, but you'd have to split it into two separate integrals and then add. And if I can avoid doing that, I'm definitely going to avoid doing that. So I would recommend against using horizontal representative rectangles, but if you wanted to try that, just again in the spirit of figuring out how to make things work and all that good stuff, highly recommend that. Okay, so instead of doing that, I am going to use a vertical representative rectangle. The reason why I'm going to use a vertical representative rectangle is because, goodness, there we go. For all of these vertical representative rectangles, the height is going to be determined by e to the negative x squared minus 1 minus cosine x. In other words, I'm not going to have to split. So the top of the rectangle and the bottom of the rectangle will be consistently determined by the same two curves. No need here to split up into two separate integrals. So for question A, finding the region of R, I would write integral from somewhere to somewhere, I don't know yet, and these would all be dx thick, and so it would be a dx integrand. And then, maybe I would figure out my limits of integration. I'm going to start accumulating here on the left at 0, and we'll finish accumulating over here on the right at the intersection point. So hopefully you use your calculator to find that intersection point. And that intersection point, unrounded, I've got 0.94194408. Okay, and then to find the area, we just need to express the height times the base of course being dx. So the height would be the exponential e to the negative x squared minus parentheses 1 minus cosine x. Be really careful with your parentheses there. They do have to be there. Okay, and it did want the full area of that region, so we'd use our calculator to finish that out. And I got approximately 0.591 if you round to 3 decimals. Okay, so like I said, I would encourage you to also consider horizontal representative rectangles for no reason other than simply just exploring and messing around with this, and obviously you can see the right answer. Hopefully you already figured that out, so you'd know if you did it right, because whether you use horizontal or vertical represented rectangles, the area is the area, should be the same thing. Okay, why don't you move on to B? B says find the volume of the solid generated when region R is revolved around the x-axis. So visualize that, try to figure out what to do with that, and then you'll pause the video here, try it, and we'll see a solution here in a second. Okay, so for B, if we're going to be revolving this around the x-axis, I want you to think about what method, what structure we'd need. And to do that, we need to ask ourselves, would the solid that results from this rotation, would it truly be a solid, or would it have a hole in it? Would it be able to hold water, that kind of thing? So I think we can probably see that because of this air that I'm highlighting in blue, like this air down here, the resulting solid will, although not have a hole, it will be able to hold water. And so because of that, we would use washers. And as I've suggested before, as soon as you identify that you're supposed to be using a washer method, I suggest that you write this out as volume equals pi integral big parentheses squared minus little parentheses squared. Doing it this way guarantees that you're going to be using the washer method, which is what you're supposed to be doing. And so you're on your way to showing, really, honestly, that you know what you're doing. Hopefully all the details work out, but even if they don't, you're at least showing that you visualize this and you understand kind of the general approach to use. The next thing to consider is this going to be a dx or a dy integrand? And I would say it would be a dx integrand. Reasoning there is because the relationship between the representative rectangles and the axis of rotation is they need to be perpendicular to each other. So since we're rotating around the x-axis, we need to be perpendicular to it, creating a dx representative rectangle. So that means that everything has to be in terms of x. This also allows us then to consider our limits of integration. You know, where are we going to start accumulating? Where are we going to stop? So we're going to start accumulating over here on the far left, work our way to the right. And the good news is, from part A, we already know this. So this would be starting accumulation at 0, and we'd finish at the intersection point, which is 0.941944408. Our final task then would be to consider the two radii. So of course the radius is the distance from the axis of rotation to the appropriate function. So the big radius would maybe go from the x-axis up to there. So like we've done in class, we could look at that and say that that is, of course, a y distance. But in the very next breath, we would just substitute. And of course, for that curve, y equals e to the negative x squared. So e to the negative x squared would go there. And again, just a reminder that it has to be, the whole integrand has to be in terms of x, because the representative rectangles, representative washers are in terms of x. And then for the smaller radius, that would be maybe from here to there. And again, that is quite literally a y distance, but hopefully we would understand that in the very next moment we'd substitute. And for that curve, y equals something different. It equals 1 minus cosine x. So I'd substitute that 1 minus cosine x in for the y. And I have got a good setup here for my washer method. We would want to turn to the calculator to figure out what this actually is. And when I ran it through the calculator, I got volume equals 1.747 approximately, if you round that to the nearest thousandths place there. Okay, I hope that made sense. Hopefully that was a good explanation for you. I want to fiddle around with this a little bit more. So I want to stay on B here, and I'm going to erase all this stuff. And the question I want to ask you, I'm going to change it up, and I'm going to say, what is the volume of the solid that's generated if that region R is rotated around the y-axis? So a little bit of a different rotation there. I encourage you to pause the video, take a minute, see if you can figure it out, and then play the video and see what I get, see if we agree. All right, so for this one, we're going to be rotating this region around the y-axis this time, and so hopefully you visualized this and realized that the resulting solid would be truly a solid. There would be no hole, could not hold water, and so we'd want to consider the disk method. There is a little twist to this, though, of course. Maybe you saw that. So according to the disk method, it would be volume equals pi times integral of r squared, and it would be a dy, right, because we'd be using rectangles that are perpendicular to the axis of rotation, and those are all dy thick. And here is where we run into issues, of course. You probably saw this. Once you get down here, like we talked about a little bit before, these rectangles' length, I guess you could call it, determined by something different than the rectangles in the upper part of the region. So once we get to that dotted blue line approximately, we're going to have to switch. And so I think I'm going to say that the volume here is going to equal pi integral r squared dy plus pi integral r squared dy. And I'll just use a lowercase r to indicate that it's a different r. And yeah, so we're going to have to consider two separate integrals to figure this out. So here we go. I think the first thing we want to do is we'd want to remind ourselves about that intersection point. But this time we're not going to be looking for the x-coordinate. We're going to be looking for the y-coordinate, because we're going to accumulate from the bottom. We're going to accumulate from the bottom to the top. And so we'd want to switch our integrals around at that blue dotted line. So for that region that I've put the green representative rectangles in, I think we'd be looking at something like this. Volume equals pi integral from, and we're going to start at 0. And then I found the y-coordinate for that intersection point to be 0.41178305. And my radius there, I'll draw this in. Maybe I'll give myself a little bit more room. My radius, of course, is going to stretch from this green dot over to that green dot. Oops, there we go. So that line segment would represent my radius for that part. And so quite literally, of course, that is an x. So I could put an x right there, but I'd have to recognize that my very next step would have to be substituting a y expression in for that. And so, of course, that curve is generated by this, and so I need to solve this for x. So it's going to be y minus 1 equals negative cosine of x. So it would be 1 minus y equals cosine of x. So it would be inverse cosine of 1 minus y equals x. So I need to do a little substituting there. So I'm going to put inverse cosine of 1 minus y. Okay, so if I were to stop right there, that would give me the volume generated if I revolve just the green part of the region around the y-axis. Of course, what I need to do is add the other part. So it'd be plus pi integral from, so it'd be 0.41178305, that same y-coordinate of the intersection point, and then it would be up to accumulation up to 1, up to the very top of the region there. Of course, it'd still be r squared. It's going to be a different r. It's still going to be dy. So the radius up there could be represented by this lovely pink color. Radius would stretch from there to there. And once again, if you want to be super literal about it, that's just an x distance. but it's going out there to that curve. It's got to be in terms of y, and it's a new curve, right? It's different than the other one. It's based on this right here. So I would need to take that and solve it for x. So I'd need to do natural log of y equals negative x squared, and then it would be negative ln of y equals x squared, and then I'd need to square root both sides. So it'd be plus or minus the square root of negative natural log of y equals x. So would I use the plus or the minus? I would use the plus because we're in the first quadrant. And so I'm going to substitute that in right here. So that would be positive square root of negative natural log of y. Okay, so certainly some more advanced things here when we changed b around just a little bit. But I think a worthy challenge. I'll let you plug this into your calculator and come up with the answer. But that would be, I believe, a good setup. All right. Let's see here. Let's do one more here with b. And what I want to do with this is, let me just erase all this actually. So what I want to do with b is I want to do one displaced axis. So I'm going to say, what if we took that region and we, instead of revolving it around the x or the y-axis, what if we revolve that region around the horizontal line y equals 1.5? So take a minute, think that over. What if we did revolve that region there? What kind of solid would result? And ultimately, let's try to find the volume of that solid. All right, so for this new version of B, revolving around this region around the horizontal line y equals 1.5, consider what kind of representative rectangles you'd need. They need to be perpendicular to the axis of rotation. So I think they would need to look something like this. These, of course, would would produce the solid. And hopefully you visualize this. Can you see all this air right here? So if all that air was rotated around that line as well, hopefully you can see that the resulting solid would have a big hole right through the middle. And so anytime you've got a solid with a hole through the middle of it, we need to use washers. And so as soon as I identify that, I'm going to write volume equals pi integral big R squared minus little r squared, and then we got to deal with the dx or the dy. But I would encourage you, as soon as you recognize washers, write that down. You might mess details up, hopefully you don't, but if you do, at least you show that you knew where to start, and that's good. Okay, so as far as dx or dy, hopefully we can recognize that these vertical representative rectangles would have a thickness of dx, and so it would end up being a dx rectangle. Limits of integration, I'm going to be accumulating from left to right across this region. So I'd start accumulating at x equals 0, and I would stop, I forgot, oh, there it is. Intersection point there in terms of x would be 0.9419448. Okay, so the only thing I need to do here is hopefully correctly fill in my radii. And so for the big radius stretches from this orange dot to this other orange dot. So that line segment right there would represent that big radius. It's the function that's further away from the axis of rotation. And maybe you remember in class, one of the ways you can do this is simply to take your axis of rotation minus the appropriate function. And so the function that is just determining that outer edge would be 1 minus cosine of x. This would actually give us the correct large radius. And then the small radius would be from this purple dot to this other purple dot. So that line segment there would be the small radius. So once again, I am going to determine this by taking axis of rotation minus the appropriate function, and here the appropriate function is e to the negative x squared. Okay, so once again, I think I'll just leave this as a setup. If you want to practice your Math 9 work, you are certainly welcome to do so. But this would be a good setup. Okay, let's go ahead and leave B alone, and let's just do example C as is written. So let me get rid of all this stuff, and why don't you check out example C. It says region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a square. Find the volume of the solid. So please take a minute to try that. This is the most recent thing we've been working on. Feel free to pause and then play to see a solution. All right, for C, if we are going to be using square cross-sections perpendicular to the x-axis, I'll try to three-dimensionalize this as best I can. This would be an example of looking down on one of the squares, but if we kind of three-dimensionalized it a little bit, try to give it a little perspective, maybe these square cross-sections would look something like that. This one, of course, would be a little bit smaller. This one down here would be even smaller yet. There'd be a little tiny one right there. Hopefully you can picture what this solid would look like. And I think that that's great, but I don't think that it's hyper important that you be able to perfectly picture what this would look like. This, of course, is a key phrase right here, cross-sections. We're not going to be using any rotation. Nothing's revolving around anything. There is no axis of rotation because nothing is being rotated. The solid is being created by cross-sections. So the way we'd set this up is volume equals integral, and then we'd want to set up our dy or dx. Since the cross-sections are perpendicular to the x-axis, they would be dx thick, and perhaps limits of integration would be a good place to go next. We're going to be accumulating across from left to right, so from the far left edge to the far right edge, that direction right there. So I think I'd start accumulating over here at x equals 0, and I would stop accumulating over there at the intersection point, and again that's at x equals 0.941944408. And then lastly, I'd want to get my integrand inside there correct. The area formula for a square is side squared. So the way that I would figure out the length of the side of the square, that would be stretching from this blue point to this other blue point right there. And so this blue line segment, that would represent the side length of one of the squares. Here's another one, this blue line segment from there to there, maybe from there to there. So you can see, of course, side length is changing depending on where you are in the region, and that side length would be based on the higher function minus the lower function. So this would be, for my side length, e to the negative x squared minus parentheses 1 minus cosine x. Again, the parentheses have to be there. Okay, thankfully this is calculator active. I'll use Math 9 here. Hopefully you did the same to see how this turned out. All right, after I ran this through Math 9, I got approximately 0.461. I've rounded to 3 decimal places. Okay, so if you want to do more with this, you certainly can. If you wanted to do more with C, you could make the cross-sections like triangles or semicircles or rectangles. You could do all kinds of things and just kind of invent your own question. I think that would be great. Feel free to practice with this as much as you want. I'm sure you could take up your whole afternoon if you wanted to. So hope this has been helpful practice for you, and hopefully you get a chance to see you tomorrow. Have a great day.